Okay, so this lecture 12 is devoted to the discussion about multidimensional devices. So up to now we have thought about one-dimensional structure, but from today, so we will expand our discussion to multidimensional cases. So multidimensional here means that two-dimensional or three-dimensional, they can be treated in a unified manner. Okay, and let's go to the box method. Box method, or sometimes called as box integral method, is the method we will use in this course. So it has a so first of all, let's think about the equations we will use in this course. One thing we have already know is steady state diffusion equation. So although we have to consider also something like this, so time derivative of time derivative of our concentration, dopant concentration, when this becomes zero under the steady state approximation, then it simply means that at steady state the flux vector F is divergenceless. So there is no divergence of this flux vector F. And how about the Poisson equation? So of course you have not studied these two equations, but you will soon in this course. There is another equation called the Poisson equation, and yes, simply speaking, in this course, when we say Poisson equation, that just to state the equation describing the electric field. Here we have displacement vector, but we can relate it to the electric field. So simply speaking, roughly speaking, the divergence of electric field is related to the charge density at a given position. That is the form of our Poisson equation. And another one is here we have once again steady state continuity equation. So please have a look at this one, and when you make a comparison between steady state diffusion equation and steady state continuity equation, you find that they are actually quite similar. So we have divergence of a certain flux term and balanced by another one. So here we have so-called generation term C and recombination term R. So they are balanced with our divergence of flux. So of course you cannot immediately understand the importance of these two equations, but in the device simulation, not process simulation, actually they build the basic governing equations of our device simulation. Okay, so anyway, please make comparison these two or three equations and try to find out the common factors they share. So what is the common factor? You can find that there always appears the terms like this or terms like this. There is certain divergence of a vector field. It can be called as flux F, or it can be called as displacement vector D, whatever, but anyway it can be represented in this way. And here we have another one, and here we have another one, that is just a scalar field, and that is matched to 0. In the case of steady-state diffusion equation, what is it? What is the scalar field? This scalar field is identically 0. And how about the Poisson equation? In this case, it is just given by negative of the net charge density. And in the case of continuity equation, you have the net recombination term shown here. So simply speaking, all of these equations can be written in a common form, in a general form, like this. So this is once again a vector field, and this one is a scalar field. So now you understand many equations, actually all equations studied in this course can be written as this form. This is quite general, as much as we are interested with computational electronics, microelectronics, then it is quite common. And how can we discretize this equation in our real space? So this is the real space position, and in the case of 1D structure, maybe you remember this one. Yes, now R is well represented by just a coordinate x and this flux vector F can be just well represented as x directional component and x directional unit vector. So when you take this one fx, and of course this f sub x depends only on x, and here you have this component, and that gives you just partial derivative of your fx with respect to x. Of course, you have to have another thing like round fy, y, and round fz, z. However, you know that this one is identically 0, and this one is also identically 0, so you don't have to consider that. So that was thing we have done already in our 1D approximation. How about S over R? Oh, that can be well expressed as just x function of x. So in the case of 1D structure, it's not that difficult to discretize it. So it is casted into something like fx dx minus sx equal to 0. That was the thing we have already done. And in the case of discretization, what we have done was just to integrate over certain control volume, and you find that fx evaluated at your upper limit of integral minus f sub x over your lower limit in the integral, and this one gives you just integrated your source term over lower to upper. So are you with me? So everybody, please try to understand the general procedure. Although we have three-dimensional equations shown here, divergence of f is matched to the source term, but anyway that can be written as quite simple form, like in the case of 1D, then it can be written as fx upper minus fx lower plus integrated quantity s of x from lower to upper. Then it is equal to 0. That was the thing we have done up to now. So maybe you remember that everything. Then more specifically, what is your lower? The integral range was just to coordinate for your hyperposition between xi and xi minus 1, and this upper range was defined as x sub I plus half. So maybe you remember this one. And this integral can be simply written as what? Just the difference between upper and lower, and that is in our uniform case, so that can be written as also delta x. So that was the situation shown in our 1D structure. Then how can we make our even more in the case of 2D or 3D cases? So can we introduce such kind of thing, integral, in our 2D or 3D case? So actually, yes, we can do it. That is actually nothing but the box method. Box method simply means that we wanted to integrate our equation over certain range. So in the case of a previous 1D case, we have introduced certain range, upper and lower. And how about this? In this case also we have to introduce a certain range in the three-dimensional case. In the case of 1D x, then we can say this is the domain, lower, upper. But how about this? If we are talking about 2D x, x and y, then how can we set the range of the integral? Then we can think about a certain range for our integration. And in the case of a three-dimensional case, then also we can think about any strange looking thing in this three-dimensional space, and that can be used as a domain of our integral. So everybody understand? So since we are working, or we worked in 1D, the integral domain was quite simple, just one-dimensional integral. However, in the case of 2D or 3D, then the integral domain can be quite complicated. Not only just a simple rectangle or a cuboid, but we can think about many more complicated, arbitrarily shaped domain. Okay, so that's the reason why we call the integral domain as a box. So here box means that the domain of our integral, and we wanted to integral our equation. What is the equation? So divergence of f minus s equal to 0. We wanted to integrate this original equation over certain box. Then that will give us the discretized version, or not perfectly discretized, but suitable for discretization. So that is the essential point of our box method. So do you have any question? So please let me know whenever you have any question. So now let's go to the more detailed discussion. So although we call it as box method or box integral method in this field frequently, but more formal term for this method is finite volume method. So this is not related with the finite element method, but this is related with the finite volume method. And in order to apply this method, first of all, we have to predefine a set of vertices, here shown as dots. Here we have white dots and blue red dot. So this one is a special one we will consider to discretize our equation, and these white dots are just surrounding, neighboring vertex points. So first of all, we assume that these kind of a set of vertices is given. Yes, they are given, and we cannot change their points. So no, it is just treated as a given point. Then from that given point, those given points, we wanted to build a box. Everybody now understand this box will be used later for our integration. Our integration will be performed over this box. Of course, there are many different dots or vertex in this domain, entire domain, device domain. So we have to consider a box centered at a given node. For example, this box just shows the box centered by this red dot. Of course, we have another one, for example, blue dot, blue vertex. Then also for this blue one, we can also try to build another box for it. Okay, so are you with me? Simply speaking, if you have a vertex, then each vertex can have its box. So are you with me? If we have a vertex corresponding to a coordinate r sub I, then we can try to find out the omega box index with I. Okay, so therefore, if we have, for example, 37th point, then of course we can identify also certain box corresponding to that one. Any number, 100, 200, any number will give us the corresponding box. That is our assumption. Then maybe you can ask me this question. Okay, so of course we can think the relation between a vertex shown here and a box. Then who decide this box? Actually, we must define the volume of this box. This is another thing we have to do, but we will assume that anyhow we can build this omega for each node quite easily. So let's assume that the equidistance of calculated well-prepared boxes in this case. Are you all with me? So in order to apply this box method over finite volume method, first of all, we have to have a set of vertices, and each vertex should have well-defined box. Fortunately, we have a good ways to build a box for each vertex from given set of vertices. Okay, then now think about this box. Once again, this box, yes, this box has surface, and we will call it as a sub I. So simply speaking, it is the entire surface. Why we have a subscript here I? It is because this is corresponding to Ri. If we have another R sub j, then of course we can think about another box omega j, and of course its surface will be called as A sub j. Are you with me? So everything looks quite obvious. And now what I want to say is, now in its third line is, this entire surface, overall whole surface, can be decomposed into multiple pieces. For example, if you are looking at this box, seemingly a cuboid, then how many pieces can you find? You can find 1, 2, 3, 4, 5, 6. You may find 6 surfaces as a component of this entire surface A sub I. So simply speaking, say that the surface, the entire surface, can be regarded as just a sum of all of our sub or small surfaces. And finally, oh, here we have J, and J here means that the neighboring vertex nodes. So are you with me? I mean that, let me just make a simple specific example. Let's say that this red dot is labeled with the number 37, and it has 6 neighboring index nodes: 30, 31, 32, 33, 34, finally here 35. So the numbering itself is quite arbitrary, and there is no reason why we have missing 36. 36 will be found somewhere else. But anyway, now let's assume that we have certain kind of indexing system. Then what will happen? Then we can find 6 surrounding vertices, neighboring vertices, and each vertex is corresponding to each edge here, the line segment connecting two vertices, and also this edge is once again corresponding to a surface. So are you with me? So let me just summarize my discussion. So when we have a certain R sub I or certain position, then we can build a volume, a box, and the box can have its surface, and we can find many different subsurfaces, and each subsurface is corresponding to another vertex Rj, because it is the reason why we call it as Ij. So the surface which is normal perpendicular to an edge connecting R sub I and R sub j. That is shown here. So this is our logical steps to consider this box. Then a face here means that something like A sub ij is perpendicular to an edge. So which edge? So edge connecting R sub I and R sub j. That is my prerequisite for applying the box method. However, don't be afraid too much about this kind of preparation. It can be quite simple in reality. So now let's assume that we have all well prepared box. Then let's try to integrate our equation over that box. So box omega sub I. Then what will happen? We just integrate our equation. It is the left hand side of our equation, and this is the right hand side of our equation. Since the right hand side is identically 0, so integral just give us number 0. So this is quite simple, and the remaining task is just to integrate the left hand side of our equation. Yes, that is shown here. And we must apply the divergence theorem. So divergence theorem simply means that when we integrate a divergence of a vector field over certain volume, then it can be expressed as just a surface integral of the same vector field over its surface. So this is divergence theorem. So please have a look at these two terms. So our left hand side contains two terms. One is so divergence related one, and another one is just related with the scalar term. So integration of this scalar term is quite easy. Then we can just keep it here. So here we have just volume integral. Nothing has changed. How about this first term? In the case of this first term, now we have exactly same one shown here. The volume is actually omega sub I. Then now, by applying the divergence theorem, now we must have the surface of our volume omega sub I. What is it? This is denoted I sub I. So that's the reason why we have A sub I in this case. So up to now, there is nothing approximated. Everything is just straightforward application of integral. So up to now we don't have any kind of approximation. But now we have to introduce approximation. For example, this one. Discretization of the volume integral term. Actually, for example, think about this box, two-dimensional box, when we consider two-dimensional case. And let's say that here we have a certain point. Let's say this is R sub I. Then what we have to do in reality is actually calculate, in order to be really exact, then we must know the S everywhere inside this box. Then we can calculate this integration. However, everybody now understand the only information we can know in this case is just function value at this position. So instead of fully calculating this volume integral, we just make an approximation. Take the node value. Yes, now we know S defined at node R sub I, then multiply the area or volume, actually volume of our integral domain. So please don't be confused in my notation. Here, omega sub I is a scalar number corresponding to a volume. For sometimes, I just used omega sub I to represent the box itself. So omega sub I sometimes used to represent the box or volume of the box. Okay, so I will use the same thing like this. A sub I, that is actually surface. However, sometimes I will use A sub I as a area of the surface. So are you with me? So I hope that everybody can be well understood. Okay, any question? So let me take a short time, short break. So simply speaking, let me just summarize the things we have studied up to now. Simply speaking, we are now trying to our simple one-dimensional integration scheme into 2D or 3D case. For that purpose, in this slide, we have prepared the integration domain. The integration domain was called as omega sub I. And after that, we have applied the integral. And maybe somewhere here, we can find this procedure. Integral of first order derivative can be written as just difference of two boundary values. That is generalized using the divergence theorem. So simply means that first order derivative of a vector field can be written as the difference between surface values at this A sub I. That is the one we have done up to now. So now let's come back to our main discussion. Then up to now what we have done is now this volume integral term can be well approximated as just node value multiplied by the volume over our box. Yes, then the remaining task is this one. How can we make a discretization of this one? That is the remaining task. Yes. So how can we make a discretized form for surface integral? The surface, our surface A sub I, can be decomposed into multiple pieces A sub I j. Please note that what is j, and j is related with neighboring, so surrounding nodes. Therefore, now once again we can decompose this integral, surface integral over whole surface into several pieces. So what is the difference between this term and that term? The difference is the left hand side just shows the integral of this quantity over entire surface, and this right hand side says that the integration over just a small subsurface. This subsurface is, for example, A sub ij, means that the surface which is normal to an edge connecting R sub I and R sub j. So let me just come back to my box here. When we consider this box, integral over a sub I means that the integral over this entire surface. But a sub ij just shows, for example, integral over this surface or that surface. Anyway, there are 6 copies of this kind of integral. Okay, so now let me come back. Then first we calculate the integration over each subsurface, and when we make a sum of them, J runs over all neighboring nodes connected to R sub I, then we can recover the integral over entire surface. So I think that is not that difficult for you to understand this concept. So, well, then the remaining task is actually calculate this number. Then how can you calculate this number? Of course, we must understand this one. F is now no longer a scalar quantity. F is a vector quantity. So we can write down in this way. Okay, so this is a scalar x-dimensional component multiplied by our x-directional unit vector Fy, y, and Fg and g directional unit vector. In general, we have to write down in this way. However, here we have dA. What is dA? Here dA means that an infinitesimal small area which is normal to our surface. So the scalar value is corresponding to this small, infinitesimally small area, and direction is showing the abnormal direction of our surface. Let's say that if this is our sphere, sorry about this ugly drawing, but please consider a sphere, and on the sphere we are now considering small dA component. Let's say that this is the origin of our sphere. Then now this direction is always outgoing from this volume. Okay, so anyway, in general, F can have many different components: x directional component, y directional component, z directional component. However, by taking this dot product between F and dA, what is the resultant scalar number? Simply speaking, this component is proportional to, so let me just write that, a component of F which is aligned with dA. So are you with me? By calculating this dot product, the resultant scalar is just showing a component of F which is aligned with dA, because this can be regarded as just projection of our original vector F onto our dA direction. So simply speaking, let me just draw once again. Let's assume that we have a certain surface component like this. This is dA. And let's assume that on this surface, actually our F vector has this direction. So they are not perfectly aligned. However, when we calculate F dot dA, actually we calculate just F component which is aligned with dA component. If we have this unaligned component of F with respect to dA, that does not contribute to our scalar product. So are you all with me? So simply speaking, although our F, the vector field itself, can have many different or arbitrary values for three different independent axes. However, this operation just takes the component aligned to dA. Simply speaking, what is dA? What is the direction of dA? And in this case, let me just show you the concrete example. Please try to find out the direction of dA on this surface. What is the direction of this dA on this surface? Everybody should be able to answer that way. This is the direction of dA. How about this bottom surface? If we have bottom surface, then its dA should be heading this way. If you cannot understand this one, then please let me know. And how about this right side? If we are considering this right side, then we have to have dA in this way. If we are considering the left side, of course, there should be dA. Are you all with me? So, simply speaking, there are many dAs, and their direction is actually equal to what? Equal to the direction of H and direction of H, direction of H and direction of H. It is because our subsurface is perpendicular to an edge. dA is actually showing the normal direction of our subsurface or of the face. So therefore, dA direction is actually corresponding to direction of an edge. This is really an important observation. By using this observation, okay, we don't have to care about the component of F which is not aligned to this surface normal direction or edge direction. Then we are able to calculate only edge directional component of F is needed. That is quite an important observation. Maybe you can ask me, this is really general in every application of numerical analysis? Then I would say that it's not. The obvious failure of this kind of approach is Maxwell equation. If you consider Maxwell equation, then quite frequently we have to find out some terms like curl of electric field or curl of H field, magnetic field. So if we have these operator in our equation, then obviously this scheme immediately fails, because the general term or general form we are considering right now is just containing the divergence of vector field. So Maxwell equation is somewhat different form, and we cannot consider that kind of thing. And even in that case, we cannot find such kind of a simple surface integral. Okay, so however, fortunately, in the case of our course, or in majority of our computational microelectronics, the general form contains just the divergence of a vector field. So that's the reason why we are quite safe to consider this kind of approximation. So simply speaking, now we should find out the edge directional component of our vector field F. Okay, so let me just summarize today's talk. So for the ith vertex node whose coefficient is given by r sub I, then we should build a discretized form. Then when we have original equation having quite a general form, then discretized equation is simply written as this form. Here we have a dimensionality of just s. However, since we have make on volume integral, so now we have this volume term here, and also we have this term. So are you with me? So this is just first order derivative, and we multiply the volume. So that's the reason why eventually we have just multiplied area term. Here we have a volume term. Okay. Then remaining task is finding out an appropriate form of f sub ji. Oh, here we have a little more thing to be a little bit careful. Please have a look at this one. Please have a look at this one and concentrate on this component. And please concentrate on the subindex, subscript. What is the subscript shown here? Here I have explicitly write down ji. Is it equal to ij? So actually not, because this one is a vector quantity and this one is vector quantity, so therefore their direction is important. So we are considering r sub I, which is inside the box, and r sub j, which is outside the box. And the direction of dA is not connecting these 2 points from J to I. No, it's not for our dA. Our dA is always defined from escaping from the box. So this is the right direction for our dA. So when we consider field term, also we must consider the flux term from I to J. So don't be confused with this subscript. Okay, so you should be careful. So if you make this kind of confusion, then what will happen? Then in this case you will have a different sign for your flux term. So if you make this kind of confusion consistently, then you will find a systematic error. And if you make this kind of confusion in some irregular way, then you will find some irregular error in your simulation code. So please don't make any confusion when you program this program, this 1. Okay. Then now let's go to my summary slide once again. So that's it. So we have this quite general discretized equation from the general original equation. Then this one is just given from our equation. Omega sub I, the volume of a box, is also given from our given mesh point. And A sub ij, that is also given from our mesh point. Then the remaining term, or the remaining task is only to find out an appropriate form of f sub ji. Once again, this f sub ji is the component of our f, which is aligned with certain a vector ji. This is unit vector connecting r sub j and r sub I, and I is starting point and j is ending point. So everybody can understand this one quite easily. But if you have any question, please interrupt me anytime. Okay?
FJI랑 FIJ랑 그 크기로 다른 거죠?
No.
크기는 같은데.
Yes. They have the same magnitude, only having different sign. So that is really good question. So let's think about, so inspired by his good question, then let me just think about this case. Here we have 2 points. It has point Ri and Rj. Then this is the border between our omega I and omega j. When we evaluate this equation or given equation for omega I and omega j, what we have is simply given by this one. In the case of this omega I, that will make something like this. Of course, we must consider the area of A sub ij and flux of what? Flux of ji. It is because we must calculate this component. And how about this upper one, omega j? In this case, once again, we must consider A sub ij. However, in this case, we must calculate the flux heading in this way. Obviously, now the role of I and j are interchanged, so we must have f sub I j from j to I. And when you have a look at this one, there is only one single vector field that is called as f. This is a unique vector defined on this surface area. And why we have these different numbers? Because in this case we multiply this dA, and in this case we multiply this dA. Since the direction of our normal area or area vector is now the opposite, that's the reason why we have only different numbers. So quite obviously that since the direction is only the difference, we can understand Fij and Fji has a simple relation. Then
뭔가 그 서피스 밖으로 나가는 플럭스는 FIJ가 돼야 될 것 같고, 서피스 안으로 들어오는 플럭스가 FJI가 돼야 될 것 같은데 노테이션이.
the reason why, okay, so he is now asking me about the the notation, why we say fji when this is the starting point and this is the ending point. However, this is quite common in many cases. For example, let's say that in many cases that is a really good question. In many cases in physics or any kind of engineering, we can find this kind of thing. So let me just do it. This is the output or sometimes response of your system. And here we have input or sometimes excitation applied on your system. Then we must have something which makes the relation between input and output. Then how can you make this notation? Then usually, for example, when you say something like this, then it is quite easy to say out, comma, in. Then that gives you quite neat notation because you know this input and input meet each other and they are eliminated and this output comes in. So therefore it is quite common in many cases denote certain quantity to relating input and output, not in a way of input to output, but output input. This is quite a usual way. So that's the reason why I have introduced this kind of notation. So I think that students from other departments will be more familiar with this kind of notation, and anyway we should keep this kind of thing. Okay, so however that was a really good question. So normal ECS guys can have such kind of question quite naturally. Okay, and any other question? So your questions are quite important and quite interesting to all of us. So if you have any question, then please feel free to give me the question, and that will be quite good for improving your understanding.
AIJ는 그럼 말씀하신 그런 오더의 컨벤션에 영향을 안
Yes,
받는
this
건가요?
is just a scalar quantity and just area. So actually we must, that is quite also good question. So actually we must calculate this one. Then this can be decomposed into this way. This dA is decomposed into scalar area. This is not related with any kind of direction, and finally we can introduce a certain direction connecting initial point and final point. And now you understand this calculation is done by f times our unit vector connecting j and I and multiplied by our dA. And this one was denoted as f sub ji, and now we have a purely area without having any kind of direction component. So now in this quantity, this area, whether I is starting point or j is starting point, that doesn't matter. That's the reason why here we have, although here we have a sub ij and here we have I sub j, but they are equal to each other. Of course, if I wanted to make it more beautiful, then maybe there is a way like this, a j I, but whatever, that doesn't matter because the interchanging the indexes in this case doesn't make any difference. Okay? Also, that was quite good question. Then now let's go to the real concrete example of Laplace equation. So I hope that everybody already know the Laplace equation. Laplace equation is simply written as this form. Laplacian of our certain solution scalar field R should vanish. This is the Laplace equation. And now we know that this Laplacian operator can be written as this way. Laplacian operator is simply given by taking gradient first and once again taking the divergence later. That is the Laplacian operator. So now when we identify this gradient of phi as a flux term f, now it can be written as simply divergence of f equal to 0. What is it? This fits our general form, okay, without any kind of source term, no source term in it, okay. So there is no source term and flux can be simply written as gradient over our solution vector phi. Then let me just calculate this f sub ji. So f sub ji, in order to calculate this one, we must evaluate f times the normal vector connecting Ri and Rj. Then you know this one is simply given by phi and a times ji. How can we calculate this number? This number is simply well expressed as this one. Here, please have a look at. Here we have a position Ri, and here we have a position Rj, and all over this domain there is always R well defined. However, we are not talking about the general case, but just the average change along this line. So simply we can make quite a good 1D approximation. Here we can say that here Rj and here we have Ri. So taking these two numbers and taking the distance between two positions, that's enough to calculate this f sub ji. So you can see that here I just introduced this one divided by distance between two nodes. Oh, what is it? Phi sub here, phi sub j simply means that phi at r sub j, and phi sub I simply means that phi at r sub I. Are you with me? Then when you just use this f sub ji, then simply speaking, the discretized Laplace equation is in this way. A sub ij, you should be able to calculate this area, and distance between two points, you should be able to calculate this distance, and the remaining task is just taking the difference of two neighboring function values, then multiplying certain number. However, this certain number is already given when you fix your vertex points. Okay, so everybody, are you with me? Then now let's go to the boundary condition. Up to now, we have thought about the Laplace equation. However, Laplace equation itself cannot be used to calculate the concrete solution. We must consider Dirichlet boundary condition. So, although we have some statement here, then simply go to this diagram. My recommendation is, first, construct your Jacobian matrix and residual vector for the Laplace equation. First, consider this Laplace equation. Only after that, for vertex nodes for the Dirichlet boundary condition, just delete your previous equation and superimpose the Dirichlet boundary condition. That's it. And let's consider an easy example. Here we have a two-dimensional structure. I think that maybe this is the simplest thing we can imagine in the case of a 2D case. Here we have 6 points. 1, 2, 3, 4, 5, 6. And these triangles means my way to make a certain way to visualization. And I wanted to ask one simple question. Please try to answer. Let's consider Ri located here. Then please try to find out your box. What is your box? If you say, okay, this triangle is my box, then you are missing the point. For this R sub I, your box should be this one. This one is your box. Why? Why it is your box? Because it has two neighboring points. Yes, here directly connected one, and your box should be constructed in this way. If you say this is all of your box, then in the edge connecting these 2 points, all of them is just assigned to your Ri. It's not fair from the viewpoint of this neighboring R sub j. At least when we consider two vertices, then we should be balanced between them. So what is the good border point between two vertex points? Maybe this midpoint would be a well-balanced border point between them. How about this one? If we have 2 points, maybe this one will be a fair point to divide the region into many boxes. So now you can just learn this way. So that will be the box for this Ri. Let me just repeat this way once again for this guy. If we consider this guy, then what will be the appropriate box? The box, now it has also other 2 neighboring points here. Then we can once again take the midpoint and take the midpoint. Then you will immediately find that this is the good box for this point. And let me just repeat again and again. How about this guy? If we consider this guy, then maybe this is the midpoint, and this is the midpoint, and this is the midpoint, and by connecting these surfaces generated from this midpoint, then we are saying that this black shaded area is good for the these black points. And if you follow this kind of thing, you find many things. For example, if we are having this one, then that will be the box. Finally, we have two more. Then let me just do it. If we have this point, then that will be box for it. And finally, we have this green point, and for green point we have this box. This kind of division is quite common, and you can immediately understand the rule. The rule is you have neighboring edges and try to find out the midpoint and make a certain point which is perpendicular to this edge. Then by considering all kinds of these small surfaces, then you can build the final block or box. Then now let me just consider once again the boundary conditions. Here we have boundary conditions. The boundary condition is like this. Here we have 2 points, here and there. For these upper 2 points, please assign number 1. Then you have 2 bottom points, here and there. For them, please apply number 0. And the only 2 points you must solve Laplace equation is shown here. For these 2 internal points, please apply your Laplace equation. Then now you have your homework 11, although we are in lecture 12, but we have one missing homework. Problem 1. This problem is not for numerical result. Instead, explicitly write down the Jacobian matrix for this system. So you must draw or show a 6 by 6 matrix. Of course, in order to do that, first you must identify each node with a unique index. This is just incomplete statement. So first identify each node with a unique index, then please show the 6 by 6 Jacobian matrix. After that, your problem 2 is just to implement the above matrix in your code and solve the Laplace equation. So, of course, what should be the answer? The answer should be, everybody understand that since upper part is 1, lower part is 0, so you must have half and half for your solution value 5. So that is quite trivial, really trivial, but anyway, please try to solve this problem. Once you can solve this problem, then extend it to more general cases. That is not that difficult, so you can do it. So this is, I think that this is the minimal set or minimal equation we can consider in this lecture. Okay, so are you with me? And do you have any question on this homework problem?
뉴만 컨디션이라는 게 물리적으로 그러니까 그냥 뉴메리컬하게는 여기 주변 값들이 얘랑 같아야 된다는 거잖아요. 근데 물리적으로 생각해 봤을 때 내가 보고 있는 도메인 물리량들도 다 똑같다는 걸 얘기를 하는데 그런 상황이 실제로 가능한가요? 그러니까는
Oh yes, you are quite good. Your question is quite good. So think about this one. If we are considering such kind of PN junction, yes, this is PN junction. Yes, this is PN junction, and usually what we do in our actual simulation is take the simulation domain in this way. Yes. Now we assume we must solve our transport equation within this red box. Then obviously homogeneous Neumann boundary condition means that there is no flux and there is no flux in this direction. Also there is no flux in this direction and in this direction. So if we are far away from this PN junction, then we assume that every quantity is just homogeneous along this way and this way, because you know this is just hot place is only located here and quite far from this hot place, then everything will be just homogeneous. So therefore, a homogeneous Neumann boundary condition can be applied when certain kind of physical quantities does not vary quite rapidly. So you are quite right. This is quite important condition. And also when we apply this kind of homogeneous Neumann condition, we should be careful. If you say, instead of that, if you say, I will use this kind of small box for uh, our how can I say simulation domain, then what will happen? Then something which is quite bad will happen, because here we have a dynamic change of variable along this way, and there is no guarantee that we have the perfectly vanishing condition. Oh, however, also we wanted to stress that, although that is quite a good question, but I wanted to give you another case we can apply homogeneous Neumann boundary condition quite safely. One example is like this. Let's say that this is your transistor. Of course, this direction is direction of carrier transport. So your source and drain are located somewhere there and somewhere there. This is the direction of carrier transport. However, if this structure is quite symmetric, it has the mirror symmetry, then we can make the symmetric plane and we can simulate only half of them, because at every position in this symmetric plane, everything is just quite symmetric, and always any kind of first order derivative vanishes. So in that case also you can apply homogeneous homogeneous Neumann boundary condition. That is one example. We can apply homogeneous Neumann boundary condition to the center of our device. That is quite important technique, because we can reduce the computational cost by a factor of 2. Okay? However, this is another story. In general, when we say this boundary is related with homogeneous Neumann boundary condition, we should be careful. That boundary should be far away from any kind of important physical uh, phenomena occur. Okay, so we have 5 minutes passed from the normal lecture time, so sorry about that. But anyway, this is your homework number 11, and I hope that will be quite interesting and quite challenging to some of you. So please try to do your best to solve this homework number 11. Okay, I will wrap up today's lecture. Thank you.